Yes, why not? Because yes, we're to the mobile networks here.
Yeah.
So it can either be an expression. This is in the settings, or it can be, and then you go into expression, and you see where it says network mode.
Okay.
Followed by a comma with another expression. There's like.
Oh, I see.
It's already in gold.
Okay. So you want.
Mobile already. Does it work? Yeah, it works. That's
weird.
Yeah, I can't. I don't know why it's working. That's not how this works.
Okay, we'll go ahead and get started again, I guess. All right. So what did you come up with for the follow set for S? Dollar sign in here? Dollar sign, yeah. Anything else? Okay, so notice S does not appear on the right-hand side at all. So 2 and 3 doesn't apply. S does not, and 4, right? S does not appear on the right hand. So just a dollar sign, yeah. How about A? How about A? Quaff, G, I hear GHPQ. And nope, not E. E is the first set. Okay, notice E is the first set of A. D. Okay. C doesn't go to lambda. Notice C doesn't. So C blocks. Right? C blocks. Right? D from following A because C doesn't go to lambda. So it could be A B. In fact, let's do this. Let's do case 2, which is the easy one, and that was the little d following the C. Okay, so that now I switch the first and follow, so follows on the top. Okay, so case 2 is a little d following the big C, which I have in there. Okay, and then I have A, B, C. A could go to lambda, B could go to lambda, but C doesn't. Really, what you have are 3 pairs: A, B, B, C, and A, C. Okay, you consider all 3 of those. So if you consider AB, then you have GH following A. If you consider BC, then you have PQ following B. And then if you consider AC, then you have PQ following A. So A's follow set is GHPQ. B's follow set is just PQ. C's follow set is D. And then you have the dollar sign. Okay? All right, before we go on to more complicated example. So you're looking at this and going, okay, what does this have to do with parsing? Okay, so you say you're going to put this into an LL1 table, and we are going to. Let's go ahead and do that. I think that's actually coming up a little later, but this is a good stopping point to actually put this information into the table so we can see actually how the parser is going to work. So what do we need for the table? We need the first set. We need the follow set. We need the grammar. Okay, so everything is based on the grammar. Okay. And then there's some rules about what goes into the table based on the first set and what goes into the table based on the follow set if you have lambdas, only if you have lambdas. Okay. And then we're going to take that table and then write a parser or simulate. We're going to just see how the parser works with the table. Okay, so what does a table look like? Well, the table, notice there are 4 non-terminals, S, A, B, and C. So the table should start with S, A, B, and C. Okay, that's the 4 terminals. Recursive descent, remember you had a function for each of these non-terminals. And LL1, you had a row for each non-terminal, okay, S, A, B, and C. There will be more examples on the table. There's a lot of information on this one. We might as well put it in here. And what goes across on the column heading? So this is like the row heading, if you will. So this is the table. All right, so what goes across the column headings are the tokens. So you can imagine your language. That's why I didn't actually do a lab for. If you take your grammar as you have it, first of all, you may have 25, 30, 50 different rows. For the tokens themselves, right? There's like 25, 30, 50 different tokens. Right, so the table is going to be huge. This one is not quite as huge. Okay, this one, what are the tokens? I have E, I have F, GH, PQ, D, okay, and here's an interesting one. There's always a column for the dollar sign. It may not have anything in it. And the line's not going straight, but you get an idea. There may not be anything under the dollar sign column, but there's a dollar sign. Sometimes we do use the dollar sign. Dollar sign just says, I don't need anything else. I'm at the end. So just give me a lambda there, okay? So here's how you set up the table. We first take our first set, right? So first take our first set and try to map into the rules. So let's do C, because that's easy. C has two rules, P and Q. C, P, and Q. Remember top-down parser. One token, one rule. One token, one rule. I'm trying to parse the C. At P, which rule am I going to pick? That one. At a Q, which rule am I going to pick? That one. If I don't have P and Q, it's not a C. Right? So if there's nothing in the table, it doesn't belong there. And B, G, H, I'll put the lambda out here so I won't forget. Okay, we're going to do something with lambda, just not yet. And A. Notice the columns match the first token, okay? And again, A has a lambda, so don't forget. Leave the lambda out there. And then S. S has 6. E, F, G, H, P, and Q. S has one rule. Okay, this is the common mistake. You may look at this, go, oh, this one is S going to E. It isn't. There is no such a rule, S going to E. S can only go to A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D. It's going in 6 times. Every single first token gets a rule in the table. In this case, the same rule. S has 6 first tokens, right? So it gets in 6 times. There's my table for the first set only. If you don't have any lambdas out here, you're done. You have lambdas out here, you're not quite done. Okay, so S does not have lambda. So forget about S's follow set. We're not going to use it. C doesn't have lambda. So that D, yeah, we're never going to see D by itself because it has to go through C first. Okay, so this one has a lambda, that one has a lambda. Then I look at the follow set of B. The follow set of B is P and Q. Follow means if I'm done looking at B, I don't need B anymore. I should see a P or a Q. So if I did see a P or a Q, that means B were to go to lambda, right? Because they follow B. I didn't have any more B, so I should see P and Q. So similarly, if I didn't need A anymore, if I see a G, H, P, or Q, okay, they can be lambdas. If I see a D, it should not be lambdas. A could never just jump to D, right? But those other four are fine. That's what the follow set tells me. They're fine, right? And then now I take care of the lambdas. This is now LL1 table. And in a little bit, we'll show you how to use this to parse. You can see how to use this to parse, pretty much, right? I got all the rules in there. So give me some tokens. Let me go, right? So before I go to that, since I do have slides, let's do another one. This one is more realistic. This one is more realistic to grammar that you might encounter. In fact, homework 4, I gave you this grammar. I gave you the LL1 table and say, okay, go parse this thing. Go parse the string. Okay, what does the string look like? String is going to start with a bracket. It's going to end with a bracket. Program is my star symbol. What's in between are statements. What can statements be? Assignment statements, ID equals expression, semicolon. If statements. What are expressions? Expressions are just IDs. ID plus, ID minus, or just ID. Okay, so pretty simple grammar. There are 1, 2, 3, 4, 5 different non-terminals or big letters. And notice this one, it has case, 1, obviously, program, case 1. It has case 2, and case 2 comes in. Here is a little letter or token following a big letter, a token following a big letter. The bracket up there is a token following a big letter, right? Okay, so those are all of my case 2s for follow set, case 3s for follow set, statements, okay, 2 big letters side by side, okay? Case 4, detail, expression, detail, expression, detail, statement, going to state, okay, you can see where there are quite a few, case 4s. That's for the follow set. How about the first set? There is a lambda, so that means I do need the follow set, 2 of them. The first set, that first column, okay? Unless the first column goes to lambda, then you have to consider the second column or the third column. Okay, so this one is a little harder to see than the little a's, little b's, little c's, but it's the same idea. See if you can give me the first set first, and then try to compute the follow set, and then we'll look at it, and we can construct a table, and then we'll work with it, either this table or this table, and see how we can use to parse. Okay? So.
Where's the follow set on the one on the board?
Oh, sorry.
Where's the follow set on the one on the board, or is that only the first set?
We put in the follow set, right?
Just
Lambdas?
point to lambda?
The lambdas, yeah. The follow sets get lambdas. The first sets get their individual rules.
So like on the one on the screen, then would you just put to lambda for all of them? It seems kind of pointless.
Which one?
Like not for anything specific, because
Here?
there's lambdas in there. I get like the one where you say A goes to E, that makes sense for the first set.
Yeah.
But it seems like if there's a lambda, you just set everything else to lambda because.
You can't set D to lambda. You shouldn't have a D without, right? D doesn't follow A. This is actually from this one.
Yeah.
Right? D doesn't follow A. And G and H doesn't follow, or E and F doesn't follow B, right? So I don't put lambda in there. So the recursive descent that we just did, we essentially put lambdas in everything. If I can't use it, you're lambda, right? But here we're actually saying, okay, well, it doesn't right if you put lambda there and it still doesn't parse, right? So only the follow sets get lambda in this case, okay? And then we'll see how to use this in a little bit. But let's take a look. Let's do this one, okay? And then this one is and then on your homework, you have one that just A's and B's and C's. And you have one that's expressions, a little bit more complicated like this. So there are a couple different grammars that ask you to do first and follow. Okay? And then we'll see what the follow set of e-tail is and the follow set of statements. And that's the rules that gets lambda. Everything else should just map to the first set.
So in a table structured like that one, where you actually want in there, you want the whole prog points to something, or do you just want the right side of the arrow?
Computing the first, I just want the first and follow set first.
So just like a list of
Mhm. So what's the first set of prog?
open brace.
Open brace, yeah, exactly. Yeah, what's the first set of expression?
ID.
ID, yeah. Right, we're still computing, right? Everything, all the tokens.
So what I'm getting confused on is that on follow, if on here it was just lambda, you would stick lambdas in the follow set on that style of table.
I don't know what the follow set is. I don't know which one to stick the lambda in.
Once you know that, you just
You just stick the lambdas with the follow. Yeah, exactly. Yeah, exactly. Yeah, once I know what the follow is, they get the lambdas. So there are only two lambdas, e-tail and statements. But we still have to compute the follow for everything because they're sort of related to each other. So you do that while I set up an example over here. So the first set should be pretty easy. Were you gonna put something up?
I was gonna say that's right.
Oh, for the first set?
For both.
For both.
Put that down.
So for statement is ID or if,
Yes.
okay. Expression is ID, e-tail is plus, minus, or lambda.
Or lambda on the first one.
Lambda in the first set, yeah, lambda doesn't go in the first follow set.
Put it away.
Okay, follow set has tokens that gets lambda productions. Okay, and then prog has a $sign
Put that. Okay.
and close bracket. Oh no, that's statement. Sorry, statements.
But that counts though, because I thought it
No,
doesn't.
not prog. A statements has a bracket after it.
Yeah, so that doesn't go in, nothing goes in the follow set on prog then because it has that ending bracket, right?
No, not in the bracket, not in the prog. Right, you're right.
So then statements, nothing in the
Statement.
follow. Or does it because it has a lambda?
Okay, so look at this bracket. You can't see my cursor. Oh, cute.
I can look at it
Okay.
here. There's a laser pointer, yellow
There's a
button.
laser pointer. Oh, really? Ah, okay. So there's that one following that one.
Yeah.
You have it?
For
Statements.
Oh,
Okay, that follows that.
okay.
Okay.
So then-
Semicolon following the expression.
okay, that's what that's doing. I'm gonna look at this again really fast.
Oh, close friend following expression.
Okay, I see what that's doing there.
And then statements and statements. So whatever for first set for statements follows statements.
Which those are the same anyways.
So
How about it
ID and
follows?
if, ID and if.
Because it follows.
Yeah.
And then
Okay.
so
You have a plus and minus.
Yeah.
That's the first set of e-tail, but it doesn't actually follow. Oh, wait. Expressions, first set, follow set goes to e-tail, e-tail goes to expression.
how does that
So
work?
I don't think you have plus minus. I don't think you have plus minus. Yeah, I don't think you have plus minus.
So
Plus minus is just in the first set.
expression. Trying to figure out why I did that.
Sure.
Yeah.
I'm gonna have that copy of my
Okay,
paper.
oh, okay, all right,
Would have go right up to check it off on Saturday or the lab,
Sure,
or I can
that's
send you an email. I mean,
okay,
it's very simple, like, you just type
Okay,
it in.
all right.
I'll
You
email
coming
tonight.
in for the senior project thing? Yeah, maybe I
Yeah.
can look at
I
it
have
then.
it scheduled for 5:40 tomorrow, so
Okay,
there is a spot open.
so I think that was from last time too.
Oh,
I
crap.
think I might have somebody there. Let me email you.
All right,
So you get off work at 5, is that?
I'm probably gonna call in sick tomorrow. So
Oh, okay, all right, just call me on the Google Hangout. I have a spot open in the middle of the afternoon, so I want change. So let me email you that.
Okay, is
So
Google
is
Hangout related to Plus? I'm not Hangout, so.
Can you do Skype? Can you
I have
Skype?
Skype,
Yeah, we
yeah.
can do Skype. Just send me your Skype ID. We can do Skype too.
All right, sounds good.
Okay,
You
all
do
right,
have
okay.
Google Hangouts with your Google Plus.
Okay.
Pretty much if you
I
have any.
searched for your name, but I couldn't find it on Google.
It's CSET Yang. CSET Yang at gmail.com.
Gotcha, okay.
Okay, all right. Okay,
So did I draw my arrow the wrong way here? Pretty.
so e-tail, okay,
Detail has
expression,
lambda.
expression, e-tail, e-tail, expression,
Yeah.
statement, statement, statements. Okay, so yeah, these are the arrows.
So that's why I reversed my arrow.
But that's just on the follow set, right?
So the arrow affects the follow set, right?
Does
so then-
e-tail follow any, does e-tail?
Details at the end of expression.
Okay, so e-tail follows ID. That does not.
Oh,
So you
because
shouldn't
there's
have the
because there's no
plus.
lambda.
I was just hoping I could-
Okay, I see. maybe.
Okay, we'll see. Okay, all right. Did everyone get the first set at least? I know follow set is a little harder to see. First set. So first set is that first column, right? So let's look at e-tail. E-tail is plus, minus, or lambda. Expression is just ID, right? Statement, ID or if. Statements is either is statements, which is ID or if, right? And then prog is that open bracket. Okay, and you do have lambdas. So this one has a lambda and that one has a lambda.
I think you added a
Oh,
line
did I
in
add
the
another
slides.
rule on this slide? Oh, that's cute. Well, this one has that one extra rule. So, so I don't know why that one got chopped off from the other one. Okay, but the same idea, right? So e-tail is plus, minus, equals, equals. Okay. So it's that first column, essentially, except for this big letter statement, which is ID and if, and it doesn't have a lambda here. So I'm not going to jump to the second column, right? So I'm just going to stay. Basically, the first column is it. There are no lambdas that mess me up here in the first column, in the first set. Okay? So anybody get anything remotely similar to that one? Maybe? Okay. Close? Okay. Pretty close. Okay. All right. Follow set. $sign is case one, which is always automatically put in. What's my star symbol? Program. Okay. Case two. Here's the token following a big letter. Bracket statements. Bracket statements. Oh, I like the laser. Okay. Semicolon. Expression. Semicolon. Expression. Okay. Close parentheses, right parentheses, expression. Oh, there it is. Okay. Case two. Case three. Case three. Again, that's supposed to be red. Statement, big letter, statements, big letter. So whatever statements first set, which is ID, if, or lambda, but never copy the lambda into the follow set. Follow statement. And that makes sense if you think about it. One statement followed by another statement. So what should follow the statement? Well, statement starts with ID or if, so you're going to have ID and if. Okay, so that makes sense when you think about one following the other, except in this case, statement itself does not go to lambda. So you're going to have ID and if, ID and if, or ID or if, ID or if. There's no lambda in there. But still, that relationship holds because of this relationship. Big letter, big letter. So whatever this first set is, follows that one. So if ID if follows the statement. Okay, case three. I think that's the only case three. I don't have another two big letters side by side. They all have something in between, right? There's no two big letters right next to each other. That's all for case three. Case four, again, you can't see the color, but I put it on the board. I'm looking for big letters all the way at the end, just with one little tricky lambda in there, right? So e-tail, so e-tail all the way, expression goes to e-tail, statement goes to statement, that's just itself. Statements go to statement and statements. Well, the top one is not interesting, it just goes to itself. But because this could go to lambda, then I'm also going to end up with a big letter right here. Okay, when you grab the slides at home, I had the blue for that one, and then the red for that one. Okay, but yeah, I'm copying them over. Okay, so, and I am copying them over. So I'm taking statements first set, a follow set, and copy into statement. Okay, statement doesn't have lambda, even though I'm copying in there. I'm not going to do anything with it, but that's okay. And I'm copying expression and e-tail are the same, so they both get this, semicolon, and then the close print. Okay, that's case 4. When you do this at home for your homework, just watch for this case. There, at least one of the problems had this. There are 2 big letters at the end, but one of them could be a lambda, so it drops out. Then you got to consider case 4 going to the last one. Okay, and other than that, it's pretty straightforward how you compute the first and the follow set. Now, what does the table look like? Okay. I'm switching gears. So hang on to this first and follow. We're going to put this information all into a table. And I kind of did the table over here, but here's a little bit more like words, descriptions. So you start with your first set. So this was the earlier, we had the first and follow for the ABC, A star, A lambda, and B lambda. So this says, okay, you insert grammar rule. So basically all 5 of these rules go into the table, at least once. Okay, how many times depends on how many first set tokens you have. And how many lambdas go in there depends on how many follow set tokens you have, if you have lambdas for that. Okay, that's the rule. And we'll see what happens if something is an LL1, is when the tables get a little too crowded. You're trying to put 2 rules or 2 or more rules into a cell. It cannot. The table lookup can only be 1 rule, 1 cell, right? There has to be unique, LL1. Every single token at any particular time, I know exactly what to do, because either going to have a rule or it's not going to have a rule, then I know it's not going to work. Okay, so first set, S has A, B, and C. S rule is A, big B, little c. So that goes into the rule table. Where first set tokens, A, B, and C. Did I do that? Okay, all right, yeah. So yeah, there's 3 first set tokens and 1 rule. So that rule gets repeated 3 times, just like I did on the board. That rule gets repeated 6 times, right? But I found a rule home for the first rule. So second rule, A going to little a. So it has to line up, right, with the A column, the little a, big A, little a, right? So pretty straightforward. And then big B, little b, that's pretty straightforward. Then what we don't have in there are the lambdas, right? So, all right, that's where you do the follow set. S does not have a lambda. So we're not even going to consider that $sign. Yeah, that $sign column continues to be empty. Not always. We're going to look at one where we're actually going to put something in the $sign column, right? In your homework, you're going to put something in the $sign column, right? It's not always going to be empty. A has a lambda. So let's look at A's follow set, C and B. C and B, they get lambdas. B has a lambda, but B's follow set is only C. So only C gets a lambda. A is empty. It should not go to A by that point. Okay, once you get here, so remember this is B's follow set, right? Once you pass the big A, you're looking at B now. You can only have C that's left. You should not have a little A's. You should not have, little B's for lambdas. If you have little B, then you take that rule, not the lambda rule. There are only 2 rules and only 2 tokens that could possibly use one or the other. Not A, not $sign. $sign says I'm done. I don't have any more tokens left. Well, no, you can't. If you're looking at B, you better have a token left. You can have a C left, but you better have a token left still. Right? Otherwise, we're in trouble. We don't have enough tokens to go around. Right? That's what this $sign column means. Yeah, if you can get here, if you don't need any more tokens, yeah, you can have lambdas in that column. That's fine. So this is the table. And I did a similar table on the board. Did I do, okay. Oh, well, might as well finish the table. Might as well finish the table, and then we can look at how to parse with it. So this one has a lot more stuff, right? And this one I did put in the dollar. I don't know why I have one example and some, but not others. But anyway, these are all the tokens in this example. Just a subset of the language. Okay, bracket. Let's look at the first set. Prague has one first set token. There it is. Right? The rules, one rule, one token. That's what we're looking for. That goes in there. Statements has 3 first set tokens, one of which is a lambda. And it has ID and if. I can find a home for ID and if. Well, ID and if comes from the first rule. Statement followed by more. Statement followed by more. Okay, well, they go in twice because there are 2 first tokens. Statement can either be ID or if. So they go in twice. Notice I'm not changing the rules. I'm not putting ID equals something here. I'm still using the original rules, whatever they happens to be, and just like put them into place in the table. They have to go in at least once. So I found a home for it. Okay, I'll come back to the lambda in a little bit. Statement could either be ID equals expression, semicolon, or if expression, semicolon. If expression statement. Okay, those are the 2 rules I have. They go in. Expression is ID or e-tail. And why did I do e-tail? Well, e-tail is after left factoring, right? So expression was ID plus, ID minus, ID equals. So now I left factor it, right? So there's e-tail is what's left after all these rules starts with ID. So I left factor to ensure that LL1. So there's the plus, minus, and equals. And notice the columns they fall under. On the homework and on the test, oftentimes I see people struggle with, okay, I have 3 rules, but which column do I put it under? Well, you put it under whatever that first token is. You will not put the plus expression rule under ID. They don't match, right? So that first column has to match the column. Otherwise, they're in the wrong place. Why would you put equals under if? That you're not parsing that. You're parsing equals. So whatever that rule is, that's the column heading. The first set, that's the column heading. And that's how you got the first set in the first place. Is you circle that first column and go, oh, plus, minus, equals. So you take that same 3 rules and you put under plus, under minus, under equals. Right? So first set is done. Now we'll look at our follow set, only for lambdas. And the only lambda is there and there. Statement does not have lambda. Expression has no lambda. And Prague has no lambda. So that means even though I have all kinds of stuff happening in the follow set, like this one has 3 tokens in the follow set, I'm not going to use it. There's no lambdas. So I have to have a statement. I'm not going to drop out and expecting to see the next token. Okay, so that's a good thing too, because when you have ID in the first set and ID in the follow set, and if you need to put in a lambda, then that's when it gets a little crowded. Okay. So this lambda only has this bracket, and there it is. And this lambda has semicolon and the right paren, semicolon, right paren. 2 lambdas go in there. 1 lambda goes on top. There's my table. I believe this is a table I gave you a homework for and said, okay, now use this table and go parse the string. And the string starts with bracket. Bracket. Ends with a bracket. And I think I gave you like x equals y. you have x equals z, and then do something. Notice I have no numbers in this one. I just have IDs. So it's a subset of a language. That's fine.
Can you go back?
Yeah.
At this point, we are still only at,
We're done.
this is a follow set is built into this too.
The follow set is done, right?
And this big table down here.
This big table down here is the LL1 table.
It's the LL1 table.
Okay.
Based on those. Okay.
The rows are the rules. The columns are the
Let's
tokens.
go first.
And then every single rule have found a place at least once in this table. Okay, that's what we're looking for. So if you're finding that you're not getting that, then something is not quite right. And I believe the grammars I gave you, so number one is I gave you 4 grammars and said, okay, which one is LL1? And we'll talk about that. But number 2 and number 4, the grammars themselves are LL1. So you shouldn't have, stuff happen. You shouldn't have rules like crowding in a table.
The one you did before with the ABC,
Mhm.
one you see up there.
This one?
Yeah, maybe go back to the one we're at, the current one. So like the outer curly bracket, there's only lambda, but in the other table you show where it would
Ah.
match.
Because the follow set only has the 1. Right, this is the lambda. If there's a lambda here, there's a lambda here. That means under this column, it gets a lambda, and under these 2 columns, it gets a lambda.
Yeah, I'm just looking at the table.
Okay, in the table on the previous one?
Yeah.
Okay, similarly, A has lambda and 2 columns, and B has a lambda and 1 column.
Right.
Okay, so these 2 columns get lambda, and this
But
column gets
along
lambda.
with that, you also have B goes to B.
Because that's the first set.
Got it.
Right? But I see what you mean. I think. This one, this lambda here, this one doesn't start with a bracket because the bracket is already there.
Right.
This one starts with the ID or if.
Right.
Then, this means that I don't need any more IDs and ifs. How do I get to this close bracket? That's what I'm done. I don't have any more statements, right? So similarly here, how do I get to, I don't need any more pluses and minuses and equals, I'm done. And then when I get to the print or the semicolon, and how do I get those? I got those from here. Okay, you told me what it was supposed to follow, expression, and expression also goes to e-tail. So that's what they follow, e-tail. Okay, all right, so see, when you work with this table, that's what I decided this term that we're not going to actually do a lab. Although this is, I think everybody usually, this is their favorite lab. Once you have the table figured out, this lab is fun because you're using a stack, and I'll show you how, I'm going to go through the steps on parsing this. I like this. I wrote one, again, I wrote one for the STL class that I taught. I just want to show you how to use the STL. The table itself is very, very sparse. Okay, sometimes you just notice you may have 50 tokens, but each rule, there's only one token, one rule per row, because when nothing else starts, right? Program can only start with a bracket. It doesn't start with anything else. So the table itself tends to be very sparse. So how do you represent this in a program? You usually use a map. So the key is the rule and the token and the result, right? What does it map to? It maps to the rule, and which is a string, a vector of string. And the reason I use a vector of string is you want to treat each symbol kind of separately, right? You want to treat each symbol separately, so you can be processing this bracket and process the statements followed by this bracket. And this is, the parser itself is a push-down automata. Recursive descent is also a push-down automata. Every recursive call gets put on the stack. That's how it keeps track of the stack. This particular parser will actually need a data structure stack, we need a stack to actually hold some information for us, right? And so here's a table. Once we figure out the table, we want to input this table into a parser program and load them in. And the one version I did was I used a map. So I load in this information, I save it into a map so I can do a quick search, take a quick lookup. I also have my own data structure stack that I use, stack of strings that I'm pushing the symbols on. So let's see what this looks like. So here's that previous example since I have it on the board, okay? And this is a top-down parser. So you're gonna start with S, okay? This is a top-down parser. So you're starting from the start, the top, which is S. So you're gonna start with S. And you start this whole parsing process by putting S on the stack. Okay, so S goes on the stack. And you load your input, and I think this will parse. E, P, D, $sign. $, this is M-N, done. Okay, so my goal is when I'm done with everything, I'm not gonna have anything on the stack, I'm not gonna have anything in the input, and I'm done. Right, if they're both empty, fine, they're done. So I'll just do a lookup. What's on the stack is S. What's in the beginning of my input is E. Remember, this is top down. So I'm grabbing a token, grabbing a rule, and then try to match the leftmost symbol. That's why we can't have left recursion. So S, E, I'm gonna do a lookup. What's S, E?
A, B,
A,
C,
B, C,
D.
D. Okay, so A, B, C, D. That means I'm going to pop off S and put A, B, C, D on there, but this is a stack. If I put A, B, C, D on there, I'm going to try to process the D first, and that's not going to work. So I'm actually going to push them backwards. So I'm always considering try to process the leftmost symbol, hence it's LL1. I'm trying to process the leftmost symbol. So here's what's going to be on the stack. And in the program, I will usually just say C, B. Okay. This is the top of the stack, right? And then I haven't done anything to the input yet. The input is still BPD. So, but if I try to look up A and E, I should have A goes to E, right? So the right-hand side of the rule, okay, so is what I'm trying to get at. So if this A, right, were to go to E, then I'm going to pop this off. And again, I haven't done anything to the input yet, but now, of course, this is not. I have an E on the stack, E in the input. I don't even need to know that an E is a token. It has to be a token because that's my input. I don't have big letters in my input. So if they're equal, it means they have to be tokens, otherwise they cannot be equal. Pop them both, pop them off. I found a match. Okay, my input gets smaller, which is what I want. Now I'm going to grab the next input. Big B, P. What's big B, P? Lambda, because I don't have B. I don't have anything. I don't have a G or H. So lambda says you pop off B, you're replaced by lambda, which is nothing. Right? Popped off B. Okay, so now we'll continue.
Where does before you go, on that BP,
Yeah.
where does the P come from?
P. P is in my input.
The B, I got the B. Where's the P coming from?
P is in my input. Remember, I'm trying to parse the input?
Yeah.
My input is EPD.
Oh, okay, sure, okay.
So there's my P, beginning of my input, right? But I'm looking for B
Oh, I see how it goes.
right? But B
Okay.
goes, oh, well, I
Yeah.
don't really have a P,
Goes
so
lambda.
let's use a lambda. Yeah,
Got it. Okay.
okay. Then C and P, just that, right? P,
P, yeah, P.
so BP. So you can see there's some steps. P's cross out. The D's cross out. If you have dollar sign, you're done. When you don't have dollar sign, you're not done. Anytime this thing doesn't match, you try to look for something in the table, it's not there, the parser stops. There's no backtracking either, right? Because everything is on the stack. How do I know which rule, where did this come from, right? Which part of this rule was S? Well, it's all on the stack, so I can't like redo it. Oh, let's put all the tokens back and start over, right? Because I can't. It's all on the stack. That's
So,
why. This one is pretty strict, LL1. There's no backtracking.
so there's a rule there that you said, and you probably said it, I missed it, is that if the stack and the input are the same, then you ignore them.
If stack and import the same, yeah, you pop them both off.
You just ignore them.
You pop them off.
You pop them off.
Yeah.
You don't do anything with them
You don't.
because of the
You
same
match.
thing.
You found a match, right? They're gone.
Okay.
Right. So our goal is trying to get everything down to nothing, right? So yeah. Okay. So homework. On the homework, I think that gave you just the table and said, okay, there's a string, EPD dollar sign. Use the table. Tell me if they match, right? Okay, so you can do it this way. If it helps you to see stack, input, and action. Okay, hopefully it's not too huge, right? Or you could go through different stack scenario and see how they went through the stacks, okay? Why would something not be one? Well, this one obviously is. Do I have all the rules? At least once in the table? Yeah, they're out there. More than once, actually. Are any cells with more than one rule? No, they all just have one. Is this table one? Yes. Okay, that's how you tell. So, so number one on the homework, when I say, okay, tell me if this is one, you could go through all of this. First follow and put it in a table and says, yep, that table looks fine. Or there are actually some, the slides are kind of slightly out of place. So there's actually some sort of clues from the first and follow, or even in the grammar itself that you can look for. Okay, so what are those clues? Well, if you have a lambda in your first set, okay, in this case, they all have lambdas because S itself can code a lambda. If you have a lambda in your first set, then you have the same token in your first set as the follow set. This is not LL1. What does it mean? Means that this first token, A, gets a rule. In this case, A goes to A. Okay? And because this has a lambda, I have to use the follow sets and put in the lambda rules. So there's a lambda for B, lambda for A, and a lambda for dollar sign. Okay? Then we get into trouble because now if I'm looking for A, big A, little a, I'm going to have two rules. Which one do I use? Again, I can't just say, oh, I'm just going to pick one. And if that doesn't work, at some point I'll come back to it. Or there's really no come back to it because things are off the stack. They're gone. Right? I don't want another stack to keep track of it. So, or any other storage. So this is not LL1, but we could probably see that anyway, just because this grammar is ambiguous. If I have one A, just one little A, which one is it? Is it this one? Or is it that one? Okay, so because they have lambda, so I can have the first one go to lambda, the B goes to lambda, and then take that A, or can take the A here and have both of these go to lambda. I have two trees, okay, just to parse the same input. Usually ambiguous grammars are not at all one. Well, ambiguous grammars are bad anyway, because what I do with it, they're not even, I don't even know how to parse this. Okay, so the clue you look for is if you have a lambda in your first set, and you have the same token appear in the first and follow, that means you have to use the follow. That means you end up with this situation. And the other situation, if I gave it to you, which I don't know. Oh, I didn't give it to you. Oh. The other situation is left factoring. So those are pretty obvious. That's not going to work. So the other situation, no question?
Did you mean left recursion?
No, left recursion should be gone by this point
Right.
because it's okay. Otherwise, here's the situation. I don't know, something. What's the first set of S? A, lambda. A, and lambda. So I have three rules. I have, what do I put? SA. Well, it could either be this, or it could be this. Then, okay, that's not LL1. Okay, it's not ambiguous, but it's not LL1. So how do I fix the grammar in this case? Let's factor this out. If this was a X, and the X were, S, N, B, C, S. Okay, that will be all right. Right? And then this one also has a lambda. But, so this immediately, if this is on a homework or a test, you can look at this and go, oh yeah, that's not LL1 at all. Because how do I fit two A's into rules in one cell? I only have one token, first token for two rules. Okay, so this tells me when I have three rules, I better have three first set tokens, at least three. If I have fewer, then that means it's going to get a little crowded. Okay? So this is easy to see. This case is usually a little harder to see. Just by looking at it, you might not always pick it out. But if you look at the first and follow set, yeah, lambda A, okay, that's not going to work. Okay, so those are the clues that you look at.
So how would you fix the one on the projector?
The one on the projector,
What's causing that? Is the fact
it's
that-
ambiguity.
Okay.
What's causing that is this ABA's business. Okay, all right, which is not necessary.
Okay, good.
So it doesn't do anything else. So it can just, yeah. So you can either decide you're going to have one or the other, but not as
So it's
business.
basically because A and B have lambda.
have lambdas, exactly. Yeah, what's causing it is just too many lambdas going on. Okay, so, oh, and this one I did show how to find the follow set for this, right? We have case 3, A, B, B, A, okay? Because they can all go to lambdas. First set, I think, was pretty obvious how we find that. And we also have the S going to A, case 4, S going to B because A could drop out. Okay, that's why I have two lines there. When you get the slides, it's got a blue line and a red line. Okay, so that's why S $ gets copied into A and B, because this whole thing could just be a lambda. I don't need A or B or the second A. So I could be looking at a $ and there's no tokens to match, which is fine. In this case, it just says, yeah, those are just lambdas. You don't need any more. Right? So the one that caused problem is not these. These are fine. is this cell because I have, two rules in one cell. Okay, so, and I did this kind of a similar one on the board, but this is the one oh, wow, the slides, they didn't really line up. But anyway, the stack, the input, and the action, okay? And the action is the table lookup. If you found something in the table, replace what's on the stack with that thing. If you have two things that are the same, go ahead and just pop them, remove them both, okay? If you try to look for something that's not in the table, there's an error and just stop. But if they're both, if they all pop off, everything is empty, input is empty and the stack is empty, then you're done, okay? So this is LL1 parser, that's it. If you have a table, the parser itself, unlike recursive descent, is very small. It's reusable because what's the input is the table. So I just had to write the stack code once, the code to do the table lookup once, the code to load in a table into a map once, right? As everything is reusable, whereas recursive descent, nothing is reusable. You change grammar, you have to go change the function that parses it, right? So it's very specific to that language. L1 table parser is very general. You can parse, you can give it this grammar, you can give a previous grammar, which just works just fine. Just treat every token as a string, treat every grammar rule as a string. Okay, that's it. Okay, so the LL1 parser is very short. I'll show you the actual code next time. Very short, and then it's usually people have a lot of fun writing this, but generating a table for your language, even the subset now. First of all, you're going to have like 25, 30 different rows. You're going to have like maybe 40, 50 different types of tokens, maybe. All the keywords get a column. Every operator gets a column. A comma gets a column. A semicolon gets a column. Bracket, every single thing, symbol in your language gets a column. Got this gigantic table, right? And if something doesn't work, and doesn't back out gracefully, if something doesn't work, it's just say, okay, I can't parse anymore. I'm going to stop here. And you're looking at a stack and input, you might not always know what's happening, okay? But in terms of, if everything is working, I mean, if you already have a table, this is an easy parser to write. Just dump it in, right? It's just, you already have a table. It's really easy to parse through. Very easy to give you the yes, no answer. Yep, it parses, or no, it didn't. Okay, but if you want to do error messages, you want to try to do more simple table manipulation, it's a little hard to insert yourself in the code to do that. That's why I decided I'm not going to have you implement this time. Okay, so, but I think it's still a good exercise to go through. And because next week we're going to talk about LR1 and just going to talk about it. We're not even going to go through the table. Okay, and we're just going to talk about the reverse. LR1 is top down. Okay, what goes on the stack are the left-hand side of your rules. S goes to A, B, C, D. So A, B, C, D goes on the stack. You process A, you process B, you process C, and you process D, leftmost. Next week, we're actually going to take the input and put it on a stack and hope to find an A, B, C, D when I'm done, which will lead me to S. Okay, it's got like the reverse. I'm going from the bottom up. So that's a little bit more complicated to show an example, to do by hand. But I have a tool that if you give it a grammar, it will generate that table for you, which is kind of cool.
Is the input on here, is that a line of code?
Input is your, in your case, will be your source file, your input file,
Yeah, would it be just one line of the source file that you'd be processing?
and it will be the entire source file.
The input would be.
So it won't fit in this format next week. It'll be the entire source file, right? So yeah, you wouldn't want to print the whole thing like this. Yeah, you process one token at a time. Yeah, entire source file. Yep. Okay. All right. So your homework. Let me switch gears here a little bit and talk about your lab 2, part 2. Let me share the entire screen so we can pull up the web page. Your lab 2, part 1, my only expectation is you implement pretty much the full grammar that you have with some sample code. And when you run the sample code through, it just says, yep, parses. Nope, it didn't. Okay, that was part 1. You didn't have to say, oh, you're missing a semicolon here. You forgot something here. Okay, that's part 2. That's this week. Okay, once you know there's something wrong and you have every individual rule, so you can go in and say, oh, hey, you need, something here or something there. Let's pull this up, make sure I'm not telling you lies. Oh, the resolution on this is terrible, of course. So I did put homework 4 in the final project there. And okay, so what will be helpful for part 2 as you're parsing through this is to actually print out the rules that they match. Okay, so the rule that actually gave you a function declaration, when you finally decided, oh, this is a function declaration. So you're going to have to hit there and return true at that point. So it would be helpful to just kind of write that out. So if I have this little snippet of code, and it may not be in this particular order. And that's the thing about these parsers, because they're recursive. So you might hit something on the bottom before you, right? You might hit the inner statements before you hit the loop, okay? Or before you hit the function. So this order might be reversed. Just print them out as you hit them, okay? And the other part of this is I like you to, if you have int, here, my laser. If you have int x, int y, okay? Now I know there are data decorations. Before I didn't. When I just break them up into tokens, I have no idea what x and y are because I didn't have any grammar. I didn't have any context. I didn't have any grammar. But now I know main is a function name, x is a data variable name, y is a variable name. Now I can put them into the simple table that you have from lab 1 and just put in a name there. Don't worry about, if I said don't worry about, yeah, don't have to check for types yet, okay? Sorry, this is a little small. Break this out a little bigger. Yeah, you don't have to check for types yet. So if I'm using types incorrectly, we're going to deal with that in the project. So here I just put the names X and Y into the simple table. So when you then use them in the assignment statement, X equals 10, well, have I seen X yet? X is ID, right? So and it's an assignment statement, so I know I have to declare it before I use it. So I'm going to look up in the simple table. If it isn't there, I'm going to give the user a warning. I can still keep parsing, but I want to give the user a warning. Hey, you didn't declare X. Okay, have I seen Y? Have I seen Z? In this case, I haven't seen Z yet because I never declared Z anywhere. Sorry, this is kind of messed up. Okay, so yeah, then I want to give user a warning. You haven't declared Z. What are you trying to do here? Okay, so simple table lookup. Has it in there or is it not in there? Yeah.
So do you want us to like halt operation or just spit out?
Just spit out the error message. Okay. We know it's syntactically correct if it is syntactically correct. So these are what's called semantic problems, right? You
Yeah.
haven't declared it. Or how about redecoration? You declare it more than once. C doesn't allow you to do that. So if you already have an int x, you try to do int x again down here, it won't let you do that because it's already in a symbol table. It's a variable, right? So let's not worry about scope yet either. We can deal with the scope. So the fact that there's a bracket, every time you enter a bracket, there's a scope. Okay, so you could have in x and then in x inside a bracket, in x inside another bracket. Yeah. And then,
So, is this code is going in the parser then that we wrote? Because now we know.
so now you want your symbol table and your
Yeah.
parser to work together? Yes.
Okay.
hmm Yeah. And then for the project, we're going to add types at least. So you're going to we're going to do a little bit of type checking. Okay. So,
So it should fail if you declare a variable.
so it should fail if you try to redeclare a variable, at least give them a warn error message. And if you declare something as int and you try to assign it to a string later, we can deal with that.
How do you deal with something like, let's say where you have inside the inner scope minus minus y,
Mm-hmm.
but if, say in there you were to put in int y, which would be a new
Mhm.
scope,
Mm-hmm.
exit out, open, right back up into a new one and do another int y.
Okay.
How
Yep.
do you handle that?
Okay. You don't have to handle that for lab 2, but how we deal with the scope, there's actually a simple way we deal with scope. First of all, the deck IDs are actually tied to a function. So the first scope is the main, so they belong to main. So if you have ny somewhere else, okay, we don't care. They belong to main. So the first bracket is we kind of scope it with a function. And we just got increment numbers. So in our symbol table, so on the first main is actually not global because main is a function. So when I enter this bracket, my scope number gets bumped up from 0 to 1. So this y has a scope number of 1. So let's say in this inner scope, I have another int y. Well, I enter another bracket, so now it's going to have a scope of 2. So, and this is just compilation side, right? Then on the actual, which we're not going to get to, on the actual code generation side, how do I access the first Y versus the second Y? Okay, they all go on the stack, right? Because all the memory goes on the stack. So it's the offset. So so I actually have index into where it is in memory is my first Y, and the inner Y and the outer Y, and in practice, really, as soon as you exit this bracket, yeah, I don't have that inner Y anymore because I'm gone, right? As soon as I leave a scope, right, I don't really have that anymore. So, yeah, there's some implementation
So there'd be a simple
strategies.
Go through and dump scope plus 1 once you leave it.
I could leave everything in. So in the compilation, I can leave everything in the symbol table because they're marked with scope. Also, all of this code, which we haven't done, so all of this code actually gets saved into a parse tree. So what is main? Main has a couple of data decorations. It has a couple of assignment statements, has a while loop, and has all that. So I have all of this information. So this is what I mean by one pass compilation. I'm going to open this file once. I'm going to read in everything. I'm going to save all I need to save. Symbol table, parse tree, whatever I need. So when I take this code and say, okay, now do something with it, which is the project, right? What do you do with this code? Now you know what it is, right? Maybe I can analyze the style of it. Maybe I can count how many variables it declared, try to do some analysis. Maybe I can generate assembly code, which is one of the options. Okay, I have all this information. What does an assembly code for this look like? Which is what traditional compilers do. It dumps out to assembly code, go to an assembler, and then you get executable code out of it. Right. So I may not want to dump anything yet because I may still need it. So I can save all this information and then I can decide what to do with it. Right. And that scope, one of the complexities measurements might be, well, what is the deep, how many scope, what's the highest scope number you have in your program? Why do you need that much, right? You have like 15 scope in. Well, why? Okay, it's a necessary complexity. That might be one of the measures. Right? Your program is too complex, and you've got 15 nested levels in, and you still introduce variables there. Okay, so and then this is the static scoping rules, which is what we use, but there's also dynamic scoping rules, which deals with runtime, and that's tricky. Did you cover that in programming languages class 223?
What was, what was
Scoping rules, dynamic scoping rules, static scoping rule,
vaguely?
static typing, static dynamic typing, all that. Okay. So anything static is compiler, anything dynamic is runtime, which we're not going to touch on. So anything static means I compile time on paper, I will take care of it. That's what static means, right? So I can look at this and say, okay, I'm going to do everything statically. I'm going to statically tell you if it's type correct, statically tell you if it's syntactically correct. And so I can do all that, right? Just statically at compile time. And then there are things that run time that I don't know until I actually run it. Right? But everything C is pretty much static. You got to declare everything before you can use it. The type doesn't change, not like some languages. So if I assign it to an int, okay, I'm an int. If I later assign it to something else, oh, I'm something else now, right? The dynamic typing, C doesn't really have. C is pretty, right? Pretty just, okay, you got to tell me what type it is, and that's the only one I'm going to keep. Okay, I'm not going to let you change it later. Okay, so that's lab 2. Just add a few things to part 1, part 2. Of course, if you're still working on part 1, got to get that grammar working, right? Otherwise, you're not going to have part 2. And your homework. Oh, got big homework. Homework for. Well, homework I think is pretty straightforward, but the project. Oh, come on, really? Where'd it go? Ah, go away. Go away. Okay. So zoom a little bit. Okay. So your project, as I say, you can work in pairs if you like. And if you end up doing most of the work and not your partner, that's your issue. Okay. If you choose someone to work with and that person is not doing the work, I probably don't need to hear about it. Okay. You can dump your partner anytime you like. It's not a JP class. I'm not going to be in the middle of managing this. Okay, so if you choose to work in pairs, then that's fine. And the traditional option is just, okay, let's do a backend. Let's write out, some sort of a target code. It could be assembler, it could be assembly, it could be, IL, whatever the target code is. You have all this information, right? Oftentimes, how the information is used, how the compiler is used, is you may have a small language for your tool, your game, or something. It just needs to have a small language in it. Okay, it's not going to drop down to assembly, but it's just going to have some language I can define, like turtle graphics, the logo language. So say that if this is my grammar for my logo language, and this is different from the language you're working with, I realize it's a different grammar. It's a small grammar, though. It's not a whole lot there. And if I have the sample code, I can obviously parse it. It's a Turing complete. I have repeat. I have if. Okay, so this is just a turtle graphics. You tell the turtle to go forward and draw, pen down, pen up, and all that. Okay, a small subset of that. Well, if this is, if I want to write a GUI tool, I want to draw. I want to write a program and have the turtle like draw a little house or something. Well, you should be able to do that. The GUI part shouldn't be that hard if you've taken a GUI class. But once I feed in my program, have you parse it and take this information and then go draw in the GUI side. Okay, so that would be a nice project to kind of show the application of how typically compilers are used. Is you just need a parser in a tool that you already have. You're doing that has nothing to do with parsing C++ necessarily, but I just need a parser. Okay, so when you have a program like this, when you have a program like this, I do have a mouse. When you, of course, the parser is going to tell you, yeah, it's syntactically correct or not, right, based on the grammar. And you can save this information into a simple parse tree. A parse tree is actually just a list of commands. Well, how many commands do I have? Okay, let's do that. Like the repeat command. How do I repeat this 4 times? It's a loop. And one of the things a lot of compiler writers will do is when you have a simple loop like this, they will do something called the loop enrolling. They will actually flatten out the loop rather than saying, okay, I'm going to remember, I'm going to repeat this 4 times. They will actually just change this statement by putting in this command 4 times, okay, and get rid of the loop altogether. So, or the end result is they don't actually see a loop, but they're actually doing the loop, right? They're just repeating the statement 4 times. But that's not required as part of this project, but I can, next week when we talk about this intermediate presentation, the semantic analysis, and that's part of the semantic analysis. You're doing a loop 4 times. Well, I'm just going to perform the statement 4 times for optimization. Okay, so how about how about a language interpreter? So your C language is probably not quite as easy as run as an interpreter because it's not an interpreter language. But if you're doing like JavaScript or something, Python-like language, okay, interpreter just says, well, just run it. Tell me what the output is. Okay, I gave you this little snippets of code. What's the output? You had input-output statements. You have some functions. You have some arithmetics. What's the output? Right, that's what interpreter does, right? It recognizes what you have, and then will actually just give you the output. So it needs to store the variables. When you have an expressions, it needs to actually evaluate them. So if everything is in there, you could do it. You can just run through it. Oh, yeah, if X is 10, and then I'm adding, doing something with X here. Okay, now I'm printing out X. Oh, X is whatever the value is. So interpreter is an option. You have compilers and interpreters that kind of go together. The 4th option is always very popular, but this one will require you to add a little bit more to your grammar because I want enough for a CST320 program, which has C in and C out, has arrays. Okay, I can give you some sample code as input. So, but the output for this, yes, I want you to take like 3 CST320 programs. Okay, this is like the whole up to the light test. Okay, how similar are these programs? So I want you to analyze them. So, and then tell me how similar they are. And some of the things could be how many symbols are in the program, the average length of the identifiers, how many loops, how many different constructs of something. This is just a small example. You can do a lot of metrics on, a lot of measurements on code. We'll even have analyzers for style. Does your code adhere to the company style guidelines? Okay, how do you do that? Well, you have to parse this thing first to see what you have. So parsers use a lot, right? So in this case, it's nothing to do with assembler, has nothing to do with, compiling C++. That's why I'm just to see how similar are they. How many different scopes do you have, right? Okay, your program, what's the maximum number of scope? Well, that could tell me based on these measurements, it can tell me if you copy somebody else's program or just change your name or change the variable name, move things around so that they don't look like the same program, but essentially the same program. There's actually a tool out there that could do that for college, for instructors. I've never actually tried. I know there's one out there, but I've always had students take this option, and it's could be kind of fun. I actually had a master's student at OSU that worked with me, took my Fortran program. The very first class I taught was Fortran. Took my Fortran program and compared them, and basically took the whole class's program and run through this analysis, which required them to, first of all, parse in Fortran. So understand what it is that they're looking at. And then finally, this LL1, I didn't have you do a lab this time. Last year, I had the students do a lab, so they knew how to do a lab. They just had to generate a table by hand. Wouldn't it be nice if you can just say, okay, here's my grammar. Okay, whatever the grammar is, there's my grammar. Right, go construct this table in a program. There's probably tools out there on the internet that do that, but this is, this is the idea of a parser generator. Basically, you gave me the grammar, I'll write you a parser. Okay, so that's nice. And there's a lot of parser generators, and we're going to look at one next week. Okay, just bottom up one instead of a top down one. So I have always, every year, I've always had students take this option because, and what does this involve? Involves you reading in the grammar, whatever it might be. I mean, it could be something quite complex like this one, right? It could be in reading in, reading in this grammar, right? And then figuring out the first set programmatically, figuring out a follow set by going through all 4 cases in the program, and then generate this table. Then this table, like I said, last year they already had a program that could read this table and then run through the parser like that. So all they had to do was take this table, dump it into their lab, and then they'd have a parser. But even writing a parser, parser is actually generic, just general. You can just write it once, but just generating this table takes a long time. Do it by hand, and you might miss something. So it'll be nice if you have 50 rules, dump it in the tool, and then just gives you a table, right? Huge table, but that's okay. It just gives you a table back. And that might be a good tool to have. I actually have one of my seniors is interested in doing some senior project. That might be something that could turn into something more. I don't know. So those are the 5 options. If you have other ideas that you think are compiler related, pretty much in the same complexity and scope as these, definitely talk to me about it. So you and your partner wants to come and talk to me about what you like to do for. So my idea here is, okay, let's kind of put everything together, right? We know how to write a parser, but what do we do about the back end? Okay, I know I have a program now, but what I do with that program, right? So that's really adding this piece on. It's like, okay, what do you do after you know what you have, right? Language translators. And in the late 90s, we did a lot of language translators from COBOL to some other language automatically. And that's painful because there's almost there's not like just taking, I'm converting from C++ to C#. Okay, well, it's pretty similar. Or, C# to Java. Well, it's almost like the same language. So there's not much to do there. you take something like so different, like Fortran or COBOL is, ancient languages, and say, oh, I really like to update it to like something more modern, like C. Oh, so there's something, it's really difficult to do. And yeah, we did it, but we worked on a tool that it's like, oh, that's really hard to do. But the idea here is still I'm going to have to parse. I have to understand what this COBOL code is supposed to do. How do I do that? Well, there's the grammar. Here's the code. Try to match them up. Once I figure out what this thing's supposed to do, then I go through the semantic analysis to figure out, okay, what is the C equivalent of a, one of these output statements, or what's the C equivalent of one of these move statements. So COBOL, if you've never seen it, it's very much English-like. So instead of saying A equals B, you have to move B into A. It was like, oh, how does that make it any clearer? But anyway, they thought that was more clear to say in English rather than, symbols. So, so just some ideas. So think about it. This is week 7. This is not due till, when is it due? Finals week. We don't have a final. Okay, we have a test 2, week 10. Then finals week, it just had the project due. We don't, so you have, 4 weeks? 8, 9, 10, 4 weeks, 3 weeks, something like 4 weeks, right? 4 weeks to do it. So think about it. Our time is running low today. Okay, I think we're done today. If you have lab 1 for me to check off, or lab 2,